Welcome everyone. In this video I'm going to show you how AutoGain works. Now, of course, it's kind of hard to compare the volume of a sound that has way less frequencies than the dry sound. But you can still hear that there is some volume compensation going on, because if you know what a low-pass filter sounds like without gain compensation, then you just know that this was definitely already a gain compensated filter. I can also show you how that would sound. Okay, so this was the filter without gain compensation, and you could hear that it was quieter. Now in the following I will tell you how I did that. If you've seen my last video, then you have seen that I already started working on my AutoGain module in that video, because it was the video where I tried to just speedrun making a whole plugin in just 2 hours. And if you've watched this video to the end, which is probably not the case because I know the statistics to my videos, then you have probably seen so you have probably not seen that I was not successful in making a plugin in 2 hours. I got pretty close, but not successful completely. One of the reasons was that I could not figure out the AutoGain situation so fast, but now I made something that I'm quite happy with, and I want to show you that. But just so you know, this might not be the final implementation of how I want to solve AutoGain in general in the future, as it's really hard to generalize this kind of stuff, and you will see why. Okay, so first of all, as you can see, this is the Overdrive Neo class, which has all of the things that are needed for the DSP of this plugin. And it has an AutoGain object called muffle gain, and it's meant to gain the muffle parameter, as the name suggests. So it gets 2 arguments. One of them is my pink noise class, which I will show you very soon, and also the argument 7, which means that there are 7 gain steps in the parameter. So say you have a parameter, and then you have a bunch of gain steps in there. In this case, 1, 2, 3, 4, 5, 6, it will be 6. After the AutoGain has been initialized, I'm calling the init AutoGain function, which just calls the evaluate function of the muffle gain. And I put that into a separate function just in case that I have multiple constructors at some point. The evaluate function gets 3 lambdas, so it kinda looks a bit similar to the normalized range that you probably all know from parameter creation, but the lambdas mean something different here. The first one is for what should the AutoGain thing do to prepare the DSP, which is just calling the prepare method of this DSP class. Then the second method is what should it do to process this, which is calling the process function, but with default values for the parameters that are not being AutoGained. And the one that is being AutoGained gets the valp parameter here. And then there is one for resetting everything, you know, just in case that something has to be reset, then it is called at the end. Now in the processing itself, we can also see the AutoGain stuff. The muffle gain object has an overloaded operator of these brackets, and I'm going in there with the sound and with the muffle parameter value. And that's all that is needed to give me the output of the filter gain. And as you can see, this commented out code was the one that I used to show you what it would sound like without AutoGain, and that's basically the difference from a high level perspective. Now let's actually look at this a little bit closer. So we can see when the AutoGain object is created, it expects something that is called pink noise, a reference of that. I decoupled it from the AutoGain itself because I think maybe there might be multiple AutoGain objects throughout a project and they don't need all their own pink noise samples. We can just use one and send it everywhere and use it. Also, there is a number gain steps argument that you've already seen, and an evaluating boolean. Now what does this class have? It has a reference to the noise, it has a vector with the gain steps and the number of gain steps and the evaluating bool, as you've already seen. So we are resizing the gain vector to the correct size and starting the evaluation with the onPrepare, onProcess and onClear functions that you've already seen from the high level perspective. In the evaluate function, I'm calling the onPrepare function with a default sample rate of 44.1 kHz because I just assume that something acts the same on every sample rate and with the size of the pink noise. Then I'm getting the RMS value from the noise and I'm making a buffer that also has the same size and only one channel because for AutoGain it's the same for both channels anyway. Then I'm looping through the gain steps and create a dummy parameter value called X in here. I'm getting the underlying samples array from the buffer and copy all of the pink noise into that buffer. Then I'm calling the onProcess function with that buffer on that channel, on that number of samples and with that parameter value. So basically the process is now running and it's processing the pink noise. Then I'm getting the RMS value from the processed pink noise as well. As you can see now we have the RMS value of just the pink noise and the processed pink noise. So the ratio between those two is the gain value that we will later use to apply gain to certain parameter values. Now it can be that there are issues in the measurements that would lead to NRMS being 0 or even none. Or maybe it could even happen that it's infinite. I don't know. In that case, I guess it might make sense to throw a gessert, but it might also make sense to just output 0 because something has to go into this gain step anyway, and it would be cool if it would just not break your ears, whatever goes in here, because this is very crucial for the safety of your ears. At the end, I'm calling onClear and setting the evaluating bool to false. So as you can see, the evaluating bool starts off with being true and at the end it's false, and it stays false from that moment on. And the reason why that is important is because whenever you are in the onProcess function of this AutoGain thingy, it will at some point also reach the point where you go into this method with the sample and the parameter value. And if we did not have the evaluating thing here in yet, we would take the gain values that are already in the array before even having calculated some and use them to calculate a sample. And that kind of makes no sense because that would be endlessly recursive in some sense. You know what I mean? So I just decided that as long as the evaluation is not over, we're just returning the sample the way it is so that there is no AutoGain. And when this is over, this is not going to be a thing anymore in the future. I'm seeing some problems with this sort of implementation because most of the lifetime of the plugin, this is going to be false. So it's kind of silly that this is always in here for all that time, as if it will still matter then. It would make more sense to come up with an implementation where this is just skipped from when the evaluation is done, but I have no idea yet. Also, I'm just generally not happy with the fact that I have to call a process in order to measure something, and this process also depends on the object itself that, you know, calls the process, because that's just the reason why there is such infinity loop recursion problems, or I don't know what you would even call these problems, but I just don't like it. And I also don't like my evaluation solution, but it works. I just don't like it. Now, you might ask yourself how to generate pink noise in the first place so that you can even write something like this. I did that by just making a pink noise struct, defining that the size is 2048, because that's also the size of wavetables in popular synthesizers, due to the fact that this number is very close to the lowest perceivable frequency in a sample rate of 44.1 kilohertz. Okay, what I did is I added std random and then Mersenne twister and random distribution, so I could make procedural white noise. So let's go into this function that generates the white noise. The thing is, I wanted this to be procedural so that it seems random and creates random noise. So noise where every frequency has the same distribution, more or less, but still always with the same seed, so that every time I'm opening the plugin, it will definitely generate the same values every single time. Because when it's just completely random, I notice that the outcome will also be slightly different every time. And that's kind of annoying, because people sometimes are very surgical with their gain matching stuff and so on. And imagine they want to, reopen the project and suddenly they have to make their gain matches again because something is just slightly off. That would be kind of annoying. Also, this is a great opportunity to just put the number 420 somewhere. And then the next method is pinken noise, which pinkens the noise. I found that on some very interesting looking web page. When you're googling pink noise, I guess pink Noise DSP. Was it this website? I think, yeah. That's a crazy website with a lot of different implementations of pink noise, and it just looks so freaking nerdy. It has a lot of weird commentary all over the place. And yeah, I just took one of these implementations and it turned out to be this. So don't ask me why, but this sort of creates pink noise from white noise. And pink noise is basically just white noise, but with a 3 dB per octave low pass filter. Yeah, that's the definition of pink noise, and that's also what happens here. I tested that, so it definitely works. Now, once you've created pink noise, you can actually keep it the way it is if you have no nonlinear processes in the DSP that you want to AutoGain against. But if you have something like a nonlinear process like Distortion or something, then you might want to tweak this pink noise to be on a certain target level. So I decided to add this code where you have this input argument where you can set a target decibel, like -6 decibel is always a good sweet spot in my opinion. So I put it as a default argument. And yeah, I just converted the target decibel to target RMS amplitude levels. And then you can calculate the gain ratio between the target and the RMS of the current pink noise. And then you're just multiplying that. So this is basically the same process as my AutoGain stuff, but just only on the pink noise to make the pink noise appear to be -6 decibels of RMS. So now that you have pink noise with a sweet spot of -6 decibels, you can also use this on distortion modules if you assume that your users are properly gain matching stuff. Sorry if that was very loud, but I just wanted to show you that this drive knob currently has no AutoGain on it. That is just the original way this Overdrive sounds like. Just in case that you haven't watched my other video, this is a tribute to MDA Overdrive, which is a very old plugin. It's from the golden age of VST plugins. You know, the age where it was still 32-bit plugins all over the place and stuff. So that was not a time where people cared about AutoGain a lot yet. And there are also some other arguments that speak against AutoGaining in Overdrive. For example, one of my guitar friends, Dominic, told me that overdrives are usually used as something that goes into another nonlinear process and then into an amp. So the gain change is actually used to drive into some other process. So if you were to AutoGain that thing, then you would manually have to add gain to get a similar effect. So that's kind of pointless in some way, or at least it's a little bit hilarious if you were to AutoGain something and then manually raise the gain to get the non-AutoGained version back. But that's just how it is. We still want to explore how to add AutoGain to this thing, because AutoGain is just very useful in general for mixing and for A/B comparing how something sounds with or without an effect. And that's just something that you have to do a lot when working in a DAW, especially considering that when you reach the point of clipping, it just clips. It's not like in the analog world where it can get to cool, colorful saturation, then it will just clip. And I'm not saying that clipping is always bad. Sometimes clipping is really cool, but not always. Okay, so as you can see, I commented out some other code, which is this drive gain code. And then let's replace this code with this one. And this will already give us a very different gain sound. As you have probably seen and also heard, this was already much more gain compensated than before. And the reason for that is probably that this is the proper way to apply AutoGain to this particular algorithm. And I just found that by accident, by just, throwing values around with the original code. Since I didn't write the original algorithm, I did not exactly know what to do, but I could just experiment with it. And then I somehow came up with this and thought to myself, oh wow, that is the perfect AutoGain for this situation. But this is not something that you can do all the time when you have an algorithm. It's just that, it depends on the individual situation, what you have to do to find a gain value that works. And we could now just go ahead and experimentally find out if it makes sense to add another AutoGain in here for the drive to make it even more gain compensated. So I'm instantiating it with a pink noise and maybe giving it, to start off with, giving it a lot of gain values so that we can be sure that there is really a gain value for every single step. I'm using linear interpolation in there, but still, it can make sense to just have all these steps and later back off with them a little bit more. Now in our init AutoGain function, I also have to init it with the other AutoGainer now, which would basically do the same things, and the only difference is that instead of taking the middle value, now it would choose the drive one. Yeah, I think, of course, we have to also use the correct name here. And then we still have to find the exact place where we have to use it. I think it would make sense to just do it in here. Drive gain with whatever comes out of here. And the second argument has to be the drive parameter, which is in here. Okay, now we have a problem because I called this thing drive gain as well. So let me just quickly rename this thing. Now this is a bit ambiguous now, but let's just keep it like that for now. It's just for testing purpose. I can still rename it later. If I'm not mistaken, then this should already have been it. Okay, it seems like it actually made it a little bit louder now. So we can just check for that by going into the evaluation function and debugging the gain values and probably also the I values so that we know in which AutoGainer we are. And then we are running that as a standalone. Okay, so now we are running it as a standalone and we can see these 0 to 7 values are the ones from the filter, starting at something around 1 and then going higher and higher to up to 1.6. So this thing increases the volume the more you dial in the muffle parameter, which makes a lot of sense. Now going to the distortion also starts at 1, goes to 1, goes up and up and up, and it goes higher and higher up to 1.7. So this thing also increases the volume, even though the drive definitely makes the signal louder and not quieter. Now, one of the reasons for that could be that these types of auto gainers are just not suited perfectly for nonlinear processes. But we could try to tweak it. Maybe just use a lower target decibel. Let's try something very drastic. And then, actually I don't want to test the sound. I just want to look at the numbers for now. So let's just put the dBg in there again. And now we see that the values are actually going down over time to 0.4. And it's still the same for the filter, because filters don't care about nonlinear processes. So now that we have a target value of minus 24 decibels, we can just go ahead and check if the sound has improved in the DAW as well. And yeah, I would say that this has dramatically improved. I will definitely keep my sweet spot on minus 24 decibels, even though I'm not sure why this signal is considered to be minus 24 decibels. Is it really that quiet? Let's check out what Ulean loudness meter says to that. Well, okay, it is quite a quiet song. I mean, it is not mixed and mastered, so obviously it is just quiet. And in some other cases, that might also be the case. But it does make sense to just have a very low sweet spot on most tools, because when you're processing your audio signal, then you're usually not doing that because it's already perfect, because you want to make it get closer to that point. So yeah, that makes a lot of sense to me still. Now you might be wondering, why does this even work? Why does AutoGain with pink noise RMS values like give me correct gain values? And yeah, the intuition for this is basically that pink noise consists of all of the frequency or of a spectral distribution that kind of resembles a sound that the human brain perceives as nice. I think a nice way to demonstrate that is by just looking at the Fletcher-Munson curve, which is a curve that looks like this. And can I have an example that does not have an alpha value in it? Thanks. Yeah, it's basically something that describes how sensitive the human ear listens to different frequencies. For example, bass frequencies need to be very loud so that we can still hear them. And there is a little bump at 4K and stuff like that, where we are the most sensitive, where we hear it even when it's very quiet. And that is very important for speech intelligibility, and a lot of people have had philosophical arguments about why this happened, and most people would agree that this is probably due to the evolution trying to give us senses that make most sense to check what our environment is telling us about the safety aspects and communication and stuff like that. Anyway, the pink noise profile, it's not as complex as the Fletcher-Munson curve, but it's sort of similar enough to give AutoGain values that sort of make sense for our ears. That always begs the question to me personally, what would happen if we actually used noise that is shaped in the Fletcher-Munson curve itself or in something similar? Alright, so this was my video about AutoGain. So if you're a developer and have watched this in order to find out how to make AutoGain for your plugins, now you can do it for filters and for saturation modules and for everything. Of course, there can be more complicated situations where like the combination of multiple parameters together has to work out to be some common AutoGain value or something, and that's definitely when my implementation breaks, because it's just one parameter and gives you an output gain, and yeah, it's not perfect. But this is just the beginning, and everyone who has a situation like this that is fairly easy to solve with this implementation can now sit back and just implement it, I guess, which is pretty cool, I guess.